Hello everyone and welcome back to the channel. Before I move on, I want to introduce to our companion website. This is bitbytoken.com. We have actually consolidated different articles based on different topics in different software engineering. We have core software engineering, data engineering, machine learning, and AI engineering. Inside each of these, if you go there, you'll be able to go through the fundamentals. We have a detailed topic listed here, and then you can read through them. There is a different article, and it will explain you in quite detail. Again, you have fundamentals here, and then you have some sample solution for different kind of design feed. And these details are all, these designs are also pretty much very extensive, very comprehensive. They start from right from functional requirement, non-functional requirements. We look at data models. Here, how things are related to each other. We try to give you sequence diagrams as well, things like that. So please go ahead, explore it, provide your feedback so that we can make it better. Thank you. Okay, let's go. So coming back to our series today. Today we are going to do something exciting, tearing down the database engine. If you're ready to move beyond definitions and understand the how database systems truly survive at a scale, piece by piece, then you are in the right place. Please remember to like, share, and subscribe to the channel for more deep dives into a complex engineering topics. We are going to open the hood of database architecture and explore the fundamental concept that allow these systems to handle massive amounts of data and traffic. Let's start our server architecture teardown with a fundamental problem: single point of failure and resource contention. From a logic perspective, it seems simple. Everything flows down through one elegant point, one connection string, one backup. But under the hood, it's a battle. Buffer pools, query planners, and IO queues all fight for the same finite resources on this single machine, including the RAM, CPU, network, and disk. This leads to a crucial failure point. 1000 users is fine. 10 million melts the hardware. The database starts to sweat, and its limitation becomes painfully clear when a single query requires joining 750 million rows. Our first solution, from a logic perspective, is vertical scaling. What this means is throwing money at the problem by adding more RAM and faster NVMe SSDs. Under the hood, this strategy is appealing because it requires zero architectural changes. It buys you time and is operationally simple. However, we quickly hit the hardware ceiling, which is our failure point. You pay a massive premium for top tier hardware, but the single point of failure remains, and all writes still funnel to one disk IO queue. This approach has diminishing returns and doesn't solve the fundamental architectural constraint. Next, we explore a logical optimization, partitioning. The logic here is the reorganizing the library. Um, it involves splitting one massive table into smaller, logical chunks within the same database instance. Under the hood, the database engine manages routing automatically through partition pruning. This drastically reduces scan times and creates smaller indexes that actually fit in memory, making query more efficient. However, the failure point remains. All disk IOs still funnel through same physical drive. Partitioning improves read performance but does not scale write throughput because the underlying hardware is still a single bottleneck. Let's compare two types of partitioning, range partitioning and hash partitioning. Range partitioning divides data based on range of values, typically chronological like 2024, 2023, 2022. The caveat is that range relies on a sequential ordering like time series logs. The major failure point here is the hot partition. In our example, today's date gets 99% of the traffic, sweating under the load, while 2019 data sits idle. In contrast, hash partitioning applies a mathematical function, say fx, to a key column, like a user ID, to determine a placement, guaranteeing even load and uniform data distribution. The caveat here is that hash relies on a uniform pseudo-random distribution, making it suitable for different access patterns. To get the best of both the worlds, we use composite partitioning. This caveat is a two-level scheme. Here, our master table is first partitioned by range, for example by year 2022, 2023, 2024. Then each year partition is further subpartitioned by hash into smaller buckets, hash 0, hash 1, hash 2. Under the hood, this is used by BigQuery and Redshift. The first level enables massive time-based query pruning, while the second level ensures even right distribution to avoid hard partitions. However, there's a caveat: increased schema complexity. Queries must align perfectly with the partition keys, or the database is forced to scan everything, negating all the benefits that we have. Another powerful optimization is vertical partitioning. The logic behind this caveat is slimming down the row size so more rows can fit into the RAM cache. We split a table into hot columns, frequently accessed column essentially, and cold columns which are infrequently accessed columns. Under the hood, this results in a massive reduction in disk IOs. By isolating frequently accessed columns, rows can become 21 times smaller, resulting in 21 times more cache hits. However, the failure point is a caveat. If the application suddenly needs to query hot and cold data together, it forces an expensive join operation, which can be costly and negate the performance gains. Now, let's clarify a critical distinction where a lot of engineers generally trip up. Partitioning is logical, sharding is physical. This is a crucial logic point. On the left, logical boundary represents partitioning, which reorganizes data within a single database instance. On the right, physical boundary represents sharding, which involves physically separating data across multiple independent servers. Under the hood, sharding crosses the machine boundary. It is horizontal partitioning applied across completely separate servers. This failure point is that treating them as the same thing leads to disastrous system pattern. Network boundary changes everything, introducing complexity that logical partitioning doesn't even face. Let's look at the anatomy of the distributed system with sharding. The logic is that each shard is fully independent database instance that has no awareness of the others. An application sends request to a shard router, which directs them to appropriate shard A, shard B, or shard C, each potentially having its own replicas. Under the hood, this provides true horizontal scale. When you add a physical machine, you add linear, predictable write throughput capacity. However, the failure point is significant. The introduction of network latency, inter-server communication, and immense distributed system complexity. This is the price of true scalability. A core component of um, a core component of sharding is the shard router. The logic is that the application doesn't know where the data lives. The router does. Under the hood, the router, such as MongoDB's Mongo's or Vitess VTGate, consults a routing table, the shard key. For example, user ID equals 847. It determines the exact map to the correct physical shard along the critical path. The failure point here is the paramount. Choosing the wrong shard key is fatal. It is the most consequential structural decision you will make, as an improper shard key can lead to uneven distribution, hotspots, and poor performance across your distributed systems. Sharding is built upon three pillars of sharding, as described by our logic here: horizontal scale out, parallel execution, and system resilience. These pillars support robust distributed systems. Under the hood, scatter gather allows parallel queries across all shards, significantly speeding up reads. Additionally, replicas allow instant promotion if a primary node dies, ensuring high availability. This contributes to system resilience. The failure point here is crucial for availability. A single shard failure is isolated, only a fraction of users are affected, while the replica promotes, minimizes impact, and maintaining continuous service. Despite its benefits, sharding introduces danger zone, cross shard joins. From a logic perspective, joins are trivial locally, but an absolute nightmare over a network. This is a classic network bottleneck under the hood. The application is forced to fetch millions of records across the network and merge them in memory, which is incredibly inefficient. The failure point offers a crucial trick. Co-locate related data. If user and post are queried together, shard them by the same key so they live on the same machine. This avoids cross-shard communication. The advice is clear. Don't do it this way. Optimize sharding to prevent these expensive network operations. Next, we face danger zone 2, the celebrity problem. The logic is straightforward. 50 million followers means 50 million rise to one exact shard when a VIP posts. This creates an extreme hotspot. Under the hood, standard hash sharding completely fails here because all traffic targets one specific hash key simultaneously, overloading that single server. The failure point highlights that hotspot will melt the individual server. To fix it, you need advanced strategies. Fan out on read, where a single write is replicated to many read-only copies. Application level caching to reduce database hits, or dedicated physical shard for VIPs to isolate high traffic entities. Then there is a danger zone 3, resharding. The logic is that adding one server using basic modulo hashing forces 80% of your data to move, which is highly disruptive. This user ID modulo num shards approach is fundamentally flawed for dynamic system. Under the hood, advanced techniques like consistent cache hashing maps keys to a continuous ring. When you add a node, it minimizes data movement to just 1 by n of the dataset, enabling minimal data movement. The failure point here is catastrophic. Moving billions of rows on a live system is catastrophic. You must design for resharding from day one, making it a fundamental architectural consideration, not an afterthought. Finally, we arrive at a senior engineer decision tree. The logic here is simple. Don't over-engineer early. Align your architecture strictly to dominant access patterns. This tree guide us. First, consider volume. The data volume dictates storage limits. Then write patterns. Write throughput dictates the sharding strategy. And finally, query patterns. Query patterns dictate the partitioning strategy. These considerations lead to a choice between a single DB, partition, or shard. The failure point emphasizes the most important skill isn't knowing every algorithm. It's knowing exactly when each tool becomes necessary. This strategic thinking is key to building resilient and scalable data system. You do provide in your comments what would you like to see next. Until next time, thank you for watching.